All right, welcome to The Explainer. Today we are diving headfirst into one of the most fascinating things in the entire universe, black holes. But we're not just going to give you the same old story. Oh no, we're going to tear down that common explanation you've probably heard a million times, show you why it's just plain wrong, and then together we'll build up a new understanding. And trust me, it's a whole lot weirder.
Yeah, I'm sure this sounds familiar, right? It's the classic definition you get in school. You squish a star down, gravity goes through the roof, and pretty soon, the speed you need to get away, what we call the escape velocity, is faster than the speed of light. And since nothing's faster than light, well, nothing can escape. It's simple, it makes sense, it feels right.
But what if I told you that entire explanation, as neat as it sounds, has a giant, gaping hole in it? A flaw so big that the whole idea of escape velocity just doesn't even apply to a black hole. Let's get into it.
So here's the deal. The whole problem comes down to a really basic misunderstanding of what escape velocity is even for. It's a concept that works for things that get thrown, like a baseball, but it's totally different for things that can push themselves. We're talking about the difference between momentum and continuous thrust.
See, escape velocity? That's all about a projectile, like a cannonball. You give it this one massive initial push, and that's it. Its fate is sealed right then and there. That initial speed is everything. A rocket, though, totally different game. It's got its own engine. It can keep on pushing, fighting gravity every step of the way. And this is the absolute key. If we're just thinking in terms of old-school Newtonian physics, the gravitational pull of this so-called black hole would be insane for sure, but it would still be a finite number. And that means a powerful enough rocket, one that could just generate a little more thrust than gravity's pull, could totally get out of there. I mean, it would be a slow, grinding climb, but eventually, it would escape. So what does that all mean? It means if black holes were just about Newtonian gravity, you could absolutely fly a rocket out of one. That popular explanation isn't just a little bit off, it's a lousy, lousy explanation. It's fundamentally broken. Okay, so to really get what's going on, we have to throw out the old playbook. We've got to leave Newton's world of simple forces behind and step into Albert Einstein's universe. And this is where things get really, really weird. We're talking about warped spacetime and general relativity. So to wrap our heads around this, let's imagine an astronaut. We'll call him Cooper, and he's about to take a one-way trip into a black hole. Now, the important part here is that we're going to watch his journey from way, way back, totally safe from all the craziness. Our perspective is everything.
Okay, so as Cooper falls closer and closer, we start to see something impossible. From where we're watching, his clock starts to tick slower and slower. This is that famous time dilation you hear about. And as he gets right up to the edge, the effect goes off the charts. I mean, right at that boundary, the event horizon, his time, from our point of view, just stops. It freezes. For us to see his clock tick one more time, we literally have to wait forever. And that right there tells you exactly what the event horizon is. It's not some kind of physical wall or a surface you could bump into. No, it's a boundary in space-time itself. It's called the event horizon for a reason. Any event that happens past that point is forever hidden from us. We can never, ever see it.
Now, just let that sink in for a second. For anything to happen, time has to move forward. But we just saw that at the event horizon, time stops. So the event of Cooper crossing the horizon, from our perspective, it can never actually happen. As far as we're concerned, he's just stuck there, frozen on the edge of the black hole for all of eternity.
But wait a minute. That's just what we see. What about Cooper? What is he actually experiencing? This is where relativity just completely messes with your head. Let's jump into his shoes for a moment.
From Cooper's point of view, everything is fine. His watch is ticking normally, 1 second per second. He probably wouldn't even feel anything weird happening, especially if it's a supermassive black hole. For him, there's no dramatic freeze frame moment. He just floats right across that boundary, the event horizon, without even noticing.
So, look what we have here, a genuine mind-breaking paradox. From our perspective, watching from afar, Cooper never ever enters the black hole. He's frozen in time. But from his perspective, he sails right on through without any drama at all. So, who's right? Did he enter the black hole or not? And the absolutely wild answer that general relativity gives us is they're both correct. Reality itself depends on your point of view. His reality and our reality are both 100% valid, even though they completely contradict each other. Wow. All right, so if we accept that in his reality, Cooper is now inside the black hole, why can't he just whip his rocket around and fly out? Remember, we already established it's not some infinitely strong gravitational pull. The real reason is so much stranger. It has everything to do with the very nature of space and time.
The moment Cooper crosses that line, the rules of the universe fundamentally change for him. Space-time gets warped so badly that space and time literally start to swap jobs. You know how for us tomorrow is a time we're all moving towards? Well, for him, the singularity, the center of the black hole, is no longer a place in space. It becomes his future. It's an appointment he can't miss, just like next Tuesday is for us.
And that right there is the ultimate prison. For Cooper to try and escape the black hole and get back to us, well, that's not about going in a direction anymore. It would be like trying to fly his rocket back to last Monday. It's impossible. You can't travel into your own past. And for him, our entire universe is now in his past. So let's just nail this down one last time. It's not some super strong force that traps you. It's the fact that once you're inside, every single path you could possibly take through space-time, it all leads to the center. The singularity becomes your inevitable future. Escaping would mean you'd have to travel backward in time. A black hole doesn't trap you with gravity, it traps you by rewriting the rules of your future.
And that leaves us with this one last really baffling idea to chew on. If, from our perspective, as observers in this universe, nothing ever really falls into a black hole, what are they? Are they just these cosmic archives with the story of everything that ever tried to fall in just painted on their surface, frozen in time for eternity? Now that is a puzzle that shows you just how bizarre and beautiful our universe truly is.